Hi there. In this video, I'll be starting chapter 6, which is about applications of integrals. And we'll only cover a very small portion of this section, just to give you a couple of ideas of things that integrals actually measure for us, but they have tons of applications. And all of these applications kind of follow a similar pattern. So I just want you to be aware of that. In future math or science classes, you may see some of these. And even though all the formulas are different, it's helpful if you understand how they're all part of the same process. So the idea is we begin by just taking some problem motivated by a geometric question or a scientific application, measuring energy, measuring a volume of some irregular shape, something like that. And then we just find a way to estimate the answer. But what you'll notice is that if you estimate the answer in a systematic way, your calculation will feel like a Riemann sum. It'll feel like you estimated it in a way where you chopped things up and you were thinking, what's a value that's true for a little while times some interval or length? And then you add all those together. And you realize, oh, well, if my estimate looks like a Riemann sum, then what I'll do is I'll take the limit of that. The limit of Riemann sums, assuming they're set up in the appropriate way, gives us a definite integral. So what emerges is there are all of these formulas for areas, for volumes, for work, for mass, for energy, for probabilities that involve integrals. So let's look at a really simple application in section 6.1, area between two curves. An area was already our motivating idea in terms of a definite integral, but here we're going to think areas between curves. So kind of the setup here is, let's suppose we're trying to find the area that is below y equals f of x, above y equals g of x, and between, say, x equals a and x equals b. So this area that I'm shading in purple, you'll notice I set it up so that the values of g are sometimes positive and sometimes negative. That doesn't matter. This region has a function on the top, a function on the bottom, and then two vertical lines matching left and right. So we might think, how could we estimate the area? And what we could do, and I'm going to do a demonstration where there's really no need to copy it. What we could do is we could estimate this using various rectangles. So I could, for example, chop up the interval from a to b, where I say, all right, a will be the same as x sub 0. And then maybe here I'll call this x sub 1, here is x sub 2, here is x sub 3, and I'll keep on going. Let's suppose I did 10 of them, 10 intervals. So b is the same as x sub 9. So I'm not putting in all the intermediate ones. And then what I could do is I could draw rectangles. I could pick some point here, and I'll call this x1 star. Again, don't copy this. I am going through a demonstration, and you just need to see where this is going. I could say, all right, well, there's a value here on the graph of g at x1 star. There's a value here on the graph of f at x1 star. And I could build a rectangle like so. My first rectangle, rectangle number 1, has an area where the base is delta x1. I'll say that my intervals are called deltas. And what is the height of that rectangle? Well, it's the height at the top minus the height at the bottom. That would be f of x1 star minus g of x1 star. So height at the top minus height at the bottom tells us the overall tallness of that rectangle. And then I could do the same thing with my second rectangle. Maybe here is the point I pick for my second rectangle. So here would be my bottom, here would be my top. I would draw a rectangle that looks something like so. How tall is this rectangle? It's top minus bottom. Don't let the negatives throw you. Whenever you know what the value at the top is and what the value at the bottom is, height is top minus bottom. It doesn't matter if they're both positive, both negative, or one of each. Just do top minus bottom. So the area of my second rectangle would be top height number 2 minus bottom height number 2 times the width of that thing. And my total, I would wind up adding them all together. I guess there are 10 of them in this version. And I know this is really messy because the details are not important. The idea is I am imagining that I could estimate the area I'm looking for by having a bunch of rectangles. And we did this before, but here the rectangles are kind of staggered. They're not all lined up along the x-axis. They're at sort of uneven heights. But still, if I did that, and I did it with enough of them, the total area of all these rectangles would be similar to this green area I'm trying to find. And this has the form of a Riemann sum. This is a function. It's a new function that I get from subtracting. So value of a function times a width, and I'm adding them all up. Our estimate is a Riemann sum, and if I wanted to make it better, what could I do? I could have lots and lots of skinny rectangles. So we take the limit of this process, and in the limit, it becomes an integral. So here's the formula you want to know. If we have a situation where a function y equals f of x marks the top boundary of a region, y equals g of x marks the bottom, and we start at x equals a and end at x equals b, then the area is given by this formula. That attempt to estimate it with rectangles turns into a definite integral of this new function, which is basically the top minus bottom function. This is measuring the height of the region as we go across. And again, let me stress this. It doesn't matter if these take negative values. Just do top minus bottom. So the idea here is really simple, but there are some wrinkles. So what do I say? Sometimes a region is merely described to us and we need to determine the limits of integration. Also, sometimes we need to break it up because there's not a consistent function on top. So what I'll urge is when in doubt, draw a rough sketch. Make sure you know what the thing kind of sort of looks like before you do an integral. So here's an example to watch. I will add a page so I can do this. So let's find the total area of the region bounded by the graphs of y equals x cubed and y equals 2x minus x squared. So hopefully we kind of know what these things look like. We know x cubed, more or less, is a curve that goes like this. And y equals 2x minus x squared, well, it's clearly a downward facing parabola. If I factored it like this, we would see that its intercepts are at 0 and 2. So let's draw a really rough picture. So y equals 2x minus x squared. It's a downward opening parabola with x-intercepts at 0 and 2. So it's going to look something like so. Y equals x cubed. Hopefully you know that. From just sort of a library of functions. Graph of x cubed, it's very steep, and then it kind of flattens out, and then it's very steep again. Right, this one is just for you to watch. Now, it looks like these graphs intersect in 3 places. what we would want to do is solve an equation to figure out where that happens. Where do these formulas give us the same thing? I'm going to move everything to one side so I can solve by factoring. And x factors out, and I have x squared plus x minus 2. And this factors as x plus 2 times x minus 1. So the intersections are at x equals 0, x equals negative 2, and x equals 1. So my picture isn't quite to scale, but this intersection here is occurring at x equals 1. You could check that that's 1 comma 1. This intersection is occurring at the origin. And then this one here is not as obvious, but it's occurring when x is negative 2, and you could check from either formula that y is negative 8. This is a schematic diagram. We accept that it is not perfectly accurate. It's just there to organize the information. And what do I want to do? I want to find the total area. So we'll notice it's basically broken up into two little regions. And you might look at these regions and think they're tall and skinny, which is true. And each region, you might look at it as having a left side and a right side. But really, you want to think of it as having a top and bottom. If I pick a point inside here, what function do I hit when I go straight up? The green one. What do I hit when I go straight down? The red one. It's reversed over here. So yes, you may naturally think of them as having a left side and a right side, but always analyze regions in terms of what is the top function and what is the bottom function, even if they're very steep. So I'll think of this as region number 1, and I'll think of this as region number 2. In order to find the area, I can do a definite integral where I'm subtracting two functions. But when I subtract them, I'm making this assumption that I know which is top and which is bottom. If they switch, I have to break them up. So to find the area of region number 1, I would do the definite integral from negative 2 to 0, because those are the x coordinates where we start this region and end this region. Right? It's from a vertical line point of view. Here's the vertical line, x equals negative 2. Here's the vertical line, x equals 0. It's in between. And then we would integrate top minus bottom. When in doubt, parentheses all over the place. For that one, our top function is x cubed, and our bottom function is 2x minus x squared. So I will attempt to do this rather quickly. We have x cubed minus 2x plus x squared. My antiderivative is 1/4 x to the 4th minus x squared plus 1/3 x cubed from negative 2 to 0. If I plug in 0, I just get 0, which is convenient. If I plug in negative 2, I have 1/4 times 16 minus 4 plus 1/3 times negative 8. So what do we have here? 4 minus 4 minus 8/3. The 4's cancel, those cancel, and I get 8/3. That is simply the area of region 1. To find the area of region 2, let's look at region 2. For region 2, it starts at x equals 0, it ends at x equals 1, and now the top function is the red one. So for region 2, it's a definite integral from 0 to 1 of 2x squared minus x squared minus x cubed. So I'm going to skip an intermediate step, but when we do the antiderivative here, well, no, I'll just for clarity, I will show this. So what do we have here? We have 2x minus x squared minus x cubed. My antiderivative is x squared minus 1/3 x cubed minus 1/4 x to the 4th from 0 to 1. If I plug in 1, that's 1 minus 1/3 minus 1/4. If I plug in 0, that's 0. So this is 12 twelfths minus 4 twelfths minus 3 twelfths, which is 5 twelfths. So our total area here is one region has an area of 8/3, one region has an area of 5 twelfths. 8/3 would be the same as 32 twelfths. So we get 37 over 12, which is a little bit bigger than 3, if I haven't made an arithmetic mistake. I did this very quickly. Don't get overwhelmed by all of this. If your reaction to all of this was that you were furiously copying all of my computations but not thinking about anything, then you're going about this the wrong way. What's really going on? We have to have some rough picture. And we have to do a computation to know for sure where these intersections occur. But the real key is to understand I can find the area of a region if I know which function is the top and which function is the bottom. Here I need to have two different regions because the top changes. For the region number 1, it begins when x is -2 and ends when x is 0. Top minus bottom, I integrate that. For region number 2, it begins at 1, ends at 0. Top minus bottom, same functions in a different order. So there's a lot of computation here, and sometimes you are going to have to do a lot of computation, but the idea here is rather simple. More often than not, this shows up in the AP on the calculator active section. They'll give you a rather interesting or unusual region, and you'll have your calculator to do something with it. Often it's a little more involved than just only find the area. They might ask you to find the area and to do other things. The concept here is much more important than the answer. So here's one for you to try. So, and it says the region shown here. So I will draw a picture for you just so it's clear what's going on. I did not type this in, but we have y equals x squared minus 5x. So y equals x squared minus 5x would be something like so. Y equals 4 root x would look something like so. I'll relabel this in a second. And y equals 5 minus x looks like so. So here's y equals 5 minus x. Here, this purple one is y equals 4 root x. And the red one is y equals x squared minus 5x. Think to yourself and then try to do the computation. How would I find the area, say, of this region? Actually, no. I'm going to make this easier. I'm sorry. Let's say this region. So pause. At the very least, think about your strategy. There is a computation that may or may not be obvious. I haven't drawn this perfectly to scale, so that will hurt you. If you want to draw this on a calculator, it might be more obvious where certain points are, but I'm intentionally not labeling them here. Try to see if you can figure out where all the important points are. So hit pause and do as much as you can for this problem. Okay, so hopefully it's very obvious that this intersection occurs at the origin and this intersection occurs at 5, 0. This one is not so clear. It's where y equals 4 root x and y equals 5 minus x intersect. Maybe just intuitively you happen to notice that 1, 4 works, and this picture is not quite to scale. Formally, you could set these equal to each other and then square each side and solve by factoring. But let's just take this as a given. So what do we notice here? This region does not have one function that is what's on top. We'll notice the red graph is always on the bottom. If I take any point inside this region and go straight down, I hit the red graph. So the red graph is always on the bottom, but sometimes I go up and hit the green graph. Sometimes I go up and hit the purple graph. So what we can do is we can break this up. Before we get to x equals 1, the purple graph is always on top and the red graph is always on the bottom. After x equals 1, green is on the top and red is on the bottom. So we have sort of the left region and the right region. So for the region on the left, it would be the definite integral from 0 to 1, because those are the x coordinates that mark where we begin and end, of top minus bottom. I will immediately write square root of x as x to the 1/2, so that it'll be easier for me to integrate that. So let's do this. My definite integral, if I bump this up, it's 3/2, and then I multiply by 2/3, so I would have 8/3 there. Minus, well, let's do the distributive law kind of in our head. Minus x squared, its integral is minus 1/3 x to the 3rd. And then we have plus 5x, its antiderivative is plus 5/2 x squared. So if I plug in 1, I get 8/3 minus 1/3 plus 5/2. If I plug in 0, I get 0. And I'll simplify that later. But this is the calculation of the shaded region to the left of that vertical line. I integrate top function minus bottom function, starting at 0 and ending at 1. How about the right? On the right, x goes from 1 to 5. My top function is 5 minus x. My bottom function is x squared minus 5x. Let's distribute that first. I know this is getting a little bit hard to follow, but I would have 5 minus x plus 5x is plus 4x minus x squared. My antiderivative here is 5x plus 2x squared minus 1/3 x cubed. If I plug in 5, I have 25 plus 50 minus 125 over 3. If I plug in 1, I have 5 plus 2 minus 1/3. So what is our total area? And again, don't get overwhelmed by the amount of calculations. Sometimes you do have to do this, but think about just what are the key steps in terms of setting it up. There will be problems that I might give you and the AP might give you where all they will ask is to present the integral that you would do. They might just say, they might just want to see you write this integral plus that integral without anything else. So my total area here would be 8/3 minus 1/3 plus 5/2 plus 25 plus 50 minus 125 over 3 minus 5 plus 2 minus 1/3. And in the interest of time and sanity, let's just leave it like that. Sorry, this was a plus. Right, This here is our area on the left. This whole thing is the area on the right. And obviously with more time we could simplify that. Okay. One thing I want to be clear here with is while we usually default to thinking of curves as given by y as a function of x, it's not required. And sometimes we'll think about it a different way. So here's an example. Let R be the region bounded by y equals root x, y equals negative 2x, and y equals 3. So let me attempt to draw a quick picture here, at least a schematic. So y equals root x looks like so, more or less. Y equals 3 is a horizontal line, something like so. And y equals negative 2x is something like so. Right, so this is just a schematic. And suppose we were trying to find the region that has those three sides. If we were to do this using our usual techniques, we would have to break it up because there's not a single function that marks the bottom of that region. So if I say, hey, what describes the top and what describes the bottom, you'd say, oh, well, there are two different bottoms. If I'm over on the left, the bottom is the green thing. If I'm over on the right, the bottom is the black thing. But sometimes we actually do want to think about left and right. I was steering you away from that before, but sometimes that works, especially if we can reverse the equations. So for example, here, y equals root x is basically equivalent to saying x equals y squared. And y equals negative 2x is basically the equivalent of saying x equals negative 1/2 y. So if I ask you, are there consistent functions marking top and bottom of this region? No, we do not have a consistent bottom. There are two different curves on the bottom. But if I say, are there consistent left and right? There are. This green thing is always what we hit if we go left. This black curve is always what we hit if we go right. So there's a different way to go about area if thinking about left and right is easier than thinking about top and bottom. So here's the idea. Let's suppose x equals f of y. So this feels really weird, but we're saying we have some equation where we can plug in y and get x by some formula. X equals f of y gives the right boundary of some curve. So maybe here is x as a function of y. This fails the vertical line test, but it satisfies the horizontal line test. And maybe here, I have x equals g of y gives me the left. And what if I want to know the area above y equals c, which is this horizontal line, and below y equals d, which is this horizontal line? Well, it's really the same kind of issue as before, but with different orientation. What we thought of before, our sort of basic setup here, if we go all the way back, so kind of the generic, I guess I never really drew a good generic picture, but our generic picture, I did draw one and then I added to it to make things a little bit more complicated. But the generic picture is that if this is A and this is B, and I have some function that's the top, and some function that's the bottom, and I want to find this region, what do? I do a definite integral starting at the number that marks the left, ending at the number that marks the right, and I integrate top function minus bottom function. What we're also allowed to do is the same process, but sort of with just a change of orientation. Here we'll do a definite integral starting at the bottom and running it to the top. And then instead of integrating top minus bottom, right, top minus bottom measures distance in a vertical way. We're going to measure distance in a horizontal way, right minus left. So that's what this formula is spelling out. If it's easier to think about right minus left, you can integrate that starting at the bottom and ending at the top. So let's see how we would do that for this region up here. What we'll notice for this region, that it starts, right, viewing this from the point of view of vertical orientation. The bottom is right here, and the bottom occurs when y is 0. So I'll actually write y equals 0 to really emphasize that I'm thinking in terms of y. And this region ends when I get to y equals 3. I don't write y equals 3. It's implied that these correspond to the same variable. And what am I going to integrate? I'm going to integrate right minus left, but expressed in terms of y. Here, I'm saying, oh, what formula in terms of y expresses what's on the right? X equals y squared. So I would write y squared. What formula in terms of y expresses what I have here on the left? X equals negative 1/2 y. I'm not writing what y is equal to, I'm writing what x is equal to. And the variable of integration here is y. So this is the integral from 0 to 3 of y squared plus 1/2 y. The antiderivative is 1/3 y cubed plus 1/4 y squared from 0 to 3. If I plug in 3, I have 1/3 of 27 plus 1/4 of 9. If I plug in 0, I get 0. So this is 9 plus 9/4, which is 9 plus 2 1/4, or 11 1/4 if we want to write it as a mixed number. So this required a change of orientation, both literally in terms of the picture and sort of mentally in terms of how we usually think about things. But once we're able to do that, we have a relatively simple integral. It would have been somewhat harder to break this up and do two different integrals. Not the end of the world. But very often, if you notice that it's easier to think in terms of a left-right orientation, that'll help. Okay, that's the end of this video.